this first derivative vanish. Okay. For example, so if x star is a critical point, and what that means is this guy is 0. Okay. So when h is sufficiently small in that this term is negligible versus this term, so the only thing that governs the behavior of this function will be the second derivative of f near this critical point. Okay. So for example, our famous friend, that is f of x equals x squared plus a constant. In this case, this guy is strictly greater than 0. If this is strictly greater than 0, what happens is, no matter what this h is, so second derivative term of Taylor expansion is kind of important because this is a quadratic term. So this is a quadratic function with respect to the increment h. H is our increment. So h can be negative or positive. But because of this function is positive, no matter where we move, okay, either along a positive direction or negative direction, so this h squared will be, like positive if h is some small increment but not 0. So the only thing governing the behavior of this function, how this function is going to move near this critical point, is the second derivative. The second derivative is greater than 0. No matter which direction we move, this thing will be positive. So which means this guy, no matter, so this guy will be greater than this guy, right? Because under the assumption that this is negligible. So this is our critical point. This is the function value at the critical point. The critical point, first derivative vanish, okay? And the second derivative is positive. So which means no matter where we move, this thing will be bigger than the function value at the critical point. So now let's have an arbitrary dimension. Okay, so we have an empty thing. So we still have this formula. So h is still a scalar. H is a scalar. But now the difference is p is a direction. So like we said last time, if we talk about some vector representing a direction, normally we mean, because the vector has two like components, like two attributes. The first one is direction, the second one is magnitude. So when we talk about this represents a direction, we have the assumption that its magnitude less. It means its magnitude is 1. And by definition, this is defined as P1 squared, P2 squared, Pn squared, and this is also square root of P transpose P. Okay. So if we assume a vector is like P1, P2, Pn. Okay. And then we have, if we move in the direction of P, this function has the following expansion, that is f of x star, okay, plus gradient of f at x star transpose P. So this is the inner product. then multiply with h, and then plus second derivative term. Here. So the second derivative term is 1/2. So we will have h squared as well. The first is we have the second derivative of f. And this is p transpose the second derivative of f of p. So this is an m by n matrix. Okay. So P is a vector. A vector is normally understood as, so this thing can be understood as a matrix with n rows and 1 column. So basically it's a column vector. And so this is n by 1, and P transpose is 1 by n. So matrix vector multiplication, n by n times n by 1, we get n by 1. 1 by n times n by 1, we get 1 by 1. So this is the number. And this number is multiplied with h squared. We have this big O of h cubed that we assume that is negligible, and that we choose our step sufficiently small so that the last term is negligible. This is the first 3 terms. So now, so in today's class, we want to introduce. So first of all, let's formally define this. Okay. So this is a matrix. So first of all, this in n dimension, this is a matrix such that it encodes all the second derivative information with respect to each variable. So let's assume x is a vector that is x1, x2 to x sub n. So this is in Rn. All right. So this is an m by m matrix. So first of all, we're going to define. The following thing. So our motivation is we want to translate what's happening in calculus, which is in 1D, to n dimension. You know, even to the dimension is so large, maybe a million dimension. You know, so for example, right now, like even the simplest machine learning model. For example, in our final project, we'll most likely use resonance 50, which has 50 million parameter, which is a large number that 20 years ago people, don't even think about. So now we want to translate that what quantifies a matrix to be positive. Okay, so this is a definition. So definition is, first of all, A is an m by m matrix. And when we talk about, like we said in the first class, this matrix, this is Hessian, right? So Hessian. When F is smooth, Hessian is symmetric, because when you take derivative with respect to x j first, xi second is equal to, we take derivative of xi first and j second. So, which means the ijth entry of this matrix is the same as jith entry of this matrix. And so the definition, the premise of this definition is important, that this matrix has to be symmetric. in order to talk about whether this matrix is greater than or greater than or equal to 0. Okay. Later we will see, because it's symmetric, so all of its eigenvalues are real. Okay. So then we can talk about eigenvalue being greater than 0, or the value of the biggest eigenvalue divided by the smallest eigenvalue when the matrix is positive, and we call that condition number, which governs the rate of convergence for gradient descent algorithm. But we'll do that later in the semester. But so what quantifies A to be positive, a matrix, the symmetric n by n matrix to be positive? So this definition is equivalent of saying for any, okay? So for any vector B, V transpose A V is greater than 0. And if this is the case, we call this A. If this is true, we say A is positive definite, or PD. So, moreover, because A is symmetric, okay, we want to add S in front of it. So we say A is symmetric, positive, definite. So this S means symmetric. So perhaps if you look at, an optimization textbook from the middle, so normally we have, okay, so we have an SPD matrix. What does that mean? SPD means symmetric, positive, definite. The matrix is symmetric, and it's positive in the sense that, okay, so V transpose AB is greater than 0, and this term right here is the analog quadratic function in n dimension. Okay, so this is ND. Now let's go back to our 2D example. Okay. So our presentation will be in ND, but our example will be in 2D. Okay. So 2D already has a much richer structure, geometric structure than 1D, so that we can talk about. Now, 2D example in lecture 1. So in 2D example in lecture 1, we kind of did, the second derivative test. So 2D example is we have a function f of xy. So we have this xy in R2. So last time we computed the Hessian. The Hessian matrix is partial f partial x twice So again, let's recall the notation that this means we take partial derivative of x with respect to partial derivative of x. Basically, we take partial derivative of x twice. So last time we considered the function that is quadratic. And then partial f partial x is 2x minus 1. And partial x twice is we take derivative of that twice we get 2. And moreover, partial f twice with respect to x and y, this is taking partial derivative of y of this partial derivative of x first, and then partial derivative of y, and then by this definition, we can easily verify that for that function this is 0 because the partial derivative of x has nothing to do with y. Okay, and then for this function, so for Hessian we denote the following thing. That is, this is A11, this is A12, this is A21, this is A22. So last time we verified several things for this specific function. For this specific function, the Hessian matrix is 2, 2, 0, 0. So 2 on the diagonal and 0 on the off diagonal. So we verified the following thing. We verified, okay, so on the diagonal we have both 2, which are greater than 0, and then we compute the determinant that is also greater than 0. And today we'll use this definition to verify, okay, it's indeed that it is the case. Because think about this. If this is greater than 0, if this matrix is positive, this just means that if this is positive, then moving, so this is our critical point. So let's assume this is our critical point. Then this term will vanish because at the critical point, the gradient is 0. So this term is gone. And then if this matrix is positive, okay, the moving from this critical point toward any direction, our function value will increase. Okay, so and we want to check the second derivative test. Actually, we learned in vector calculus. Even though the calculus textbook doesn't tell us, okay, so it's actually Taylor expansion, but if we write that explicitly, we'll see that it is the case. So now let's verify what quantifies the Hessian of 2D to be positive. So let's think about a vector UV, okay, in R2. So this is the direction. So this is like our P. This is the direction. So in the sense that this is 1. So then this P transpose, maybe I shouldn't use P. Let's change to another letter, P1, P2. Oh my gosh, they don't have any eraser.
So, quick question. I mean, we're always talking about scalar value functions. Are we going to get anywhere into like vector value functions where f is not a scalar that returns another vector that we're trying to optimize for the point in our space?
Think about this. That's
and I know it gets a lot more complicated. Yeah.
Think about this. How do we say a vector function achieves a minimum?
Well, you're going to you're trying to go in a certain direction, or because you have to define the definition of what's a maximum, what's a minimum. You're trying to define.
Yeah, but when we talk about maximum and minimum, we're talking about we can compare two values, right? But for vectors, what quantify it to be bigger or smaller? Think about this. How do we make a vector function's value smaller? How do we make a vector smaller?
Well, you're trying to go towards a certain point, I guess. I mean, you still have to have some sort of a metric on that. So you still have to get it down.
If it's a metric.
You still have to get it down to a scalar then, I guess. Okay. Yeah.
Okay. So if we want to get a metric, then it becomes a scalar. So okay. All right. Let me change this to P1, P2 because we use V there. Yeah, I don't like to look at my notes during lecture. So sometimes I don't follow the notation in the notes, but in the notes, the notation is perfectly consistent. Okay, so, okay, so let's consider this. So P1, P2, which is P transpose, A1, A12, A21, A22. And this is P1, P2. Okay, so this is getting our hands dirty to see why in ND, V transpose AV is a quadratic function. So let's compute it. So by the way, if you guys have played PyTorch, this is called so you can import the neural network interface, and if you call the function bilinear, it's exactly this function. So you call the function nn dot linear, I guess, if you guys have played the neural network, it's basic, building block, but this guy is nn bilinear. Okay. So then we compute this, right? So this guy multiplied with this, we get A11 P1 plus A12 P2. And this is A21 P1 plus A22 P2. Now we do this multiplication. So what we will obtain will be A11 P1 squared plus, so this guy multiplied with this, we'll have A21 P1 P2. And then we have, we multiply this with that, so it's plus, so it's P1, so it's A12 P2 P1. And then this multiplied with this is plus A22 P2 squared. The Hessian matrix is symmetric. A12 is A21. So what we will obtain is, this is A11 P1 squared plus 2 times, so let's say this is, A21 is A12, so it's just a name it A12, and then this is A12 P1 P2. And this is A22 P2 squared. So this is a quadratic function. This is a quadratic function in 2D. Think about so if we think about P1, P2, is x and y, this is nothing but A11 x squared plus 2A12 xy plus A22 y squared. Okay. Now let's look at the definition of the positive. This is actually better than the eraser. Yeah, I didn't realize that. When I have to erase the glasses in our house, so I found this is pretty handy. I didn't realize, Okay, so now let's look at the definition. Okay, so back to the def. So back to the def of A being SPD. So we have a key statement here, that is, no matter for what V, this thing should be greater than 0. So this for anything, okay, so for those of us that may not be very familiar with mathematical proof, this gives us some room to play with. That means we can choose whatever V we like. So for example, in this case, we choose vector. For example, we choose what? We choose P to be 1, 0. Right? This vector has unit length. Agree? Okay, so it's 1. And now let's plug it in. So P1 is 1, P2 is 0. This tells us what? This is 1. So we have A1, 1. This is 0, this is 0. So, okay. So if we choose P to be 1, 0, we have P transpose the Hessian. P is A1, 1. So in order that this matrix is positive, this has to be greater than 0. Do a similar thing. So we choose, if we choose P to be 0, 1, we do the same thing, we compute that. So P1 is not 0. So we get A2, 2. Okay. All right. So remember last class, we said, okay, so we have the 2 diagonal to be positive, then we check the determinant that is positive. Okay. So now next, think about this. Without loss of a generality, so we want to check, we move from other direction, we get positive as well. So I think that the book writer of calculus is really clever that kind of reduce very complicated problem to a very simple problem. So we pull out. So without loss of generality, let's assume P1 is not 0. So now we can pull out P1. What happens? This is A1, 1 plus. So if we pull out P1 square, we have this is 2A1, 2 P2 divided by P1, okay, plus A2, 2 P2 divided by P1 squared. Now if we look at this expression, so P1 is something not 0, so this guy is positive. Now this becomes, so if we make a simple change of variable, we let's say, R to be P1 divided by P2, then this becomes a quadratic function of R, right? You guys agree? So this is a quadratic function with respect to this variable, so if we let, say it again?
Why is the last term divided by P1? Oh wait, never mind, I'm sorry. We're good.
Okay. So what happens is so without loss of a generality, so when we consider, so when P1 is 0, we can divide by P2. The argument is similar. So without loss of generality, we let P1 be non-zero. Then what we can do is, then we can transform this P transpose Hessian P is P1 square, and it becomes a quadratic function with respect to R, that is A22R, A2 times A12R, sorry, A22R square, and 2 A12R, and plus A11. So now it's actually goes back to what we learned back in high school. That is, if we want a quadratic function, if we all to be always greater than 0. Okay, so think about this. If we want a quadratic function to be always greater than 0, so we have several cases of quadratic function. So if a quadratic function intersects with the x-axis, okay, we have two real roots, right? Because it dips below this 0, which is horizontal axis. And when it touches this axis, by touches, it's like at this point, it's tangential. So this axis is its tangential direction, so that it intersects with the quadratic function at only one point. It has a repeated real root. Okay, so this case is a discriminant. So this is discriminant delta, which is, so if x is AR squared plus BR plus C, this is what? This is discriminant is B squared subtract 4AC. Okay, so high school algebra. Lastly, if we want this quadratic function to be always positive, okay, no real roots anymore. We have only complex roots. The discriminant is less than 0. So in this case, f can dip below this f being 0. So this horizontal axis is above, which means if we want, we know that this thing is positive because under our assumption that P1 is non-zero. So we want this guy to be always positive. The discriminant has to be strictly less than 0, which means if we set it with 0, we'll get two complex roots. So it's always positive. And its discriminant is what? Is B squared subtract 4AC, which is 2A12 squared subtract 4AC, which is A11 times A22. It has to be less than 0. Okay, so last time we checked the determinant of the Hessian matrix is positive. Now let's look at the formula. Okay, this is 4 times A12 squared subtract A11 times A22. And the determinant of this matrix is A11 times A22 subtract A12 times A21. These two are equal. Okay. So it's this guy times this guy subtract this guy squared. It's exactly, so this implies the determinant of A, which is, so this thing is strictly less than 0, which means the determinant is strictly positive, and this is our third condition for second derivative test. Okay. calculus, and this is connecting the second derivative test. So these three criteria makes up the second derivative test to check if a function achieves a local minimum at a point, okay, in calculus. So it's the same thing checking. So it's equivalent. So the story behind this is, so the second derivative test, okay, we learned in vector calculus, 2 dimension. So this thing is equivalent of checking the Hessian matrix of F is positive. By a matrix being positive would mean that, the definition would just be erased. That is any vector P or V, V transpose Hessian V is positive. Okay. Actually, the calculus textbook kind of translate this into, let's say, an easier to understand language for undergrad students. But so now we know why this is the case. It's because Hessian is positive. Question? No. Any other question? Okay. So now to prepare, we will learn basically the simple method called gradient descent next week. And but let's try to answer what is the geometric meaning. Gradient and directional derivatives. Second. So notation-wise, let's still be try to be kind of formal. Okay. So f is a function from Rn to R. So for example, so in this scenario, the most likable function is this, the Elton square. So we like it very much. We use it as a regularizer all the time. With x being a parameter of the neural network. The reason to do this is because when we choose, so the heuristic of doing this, when we choose, an alpha in front of this quadratic term bigger enough, our neural network, loss function or objective function becomes a quadratic function, so its Hessian is positive and everything, can be explained. So this is the reason behind it. But okay, so the gradient of f is defined as a vector that is partial f, partial x1, partial f, partial x2, and partial f, partial xn. Okay. Okay. So for example, this is a vector in dimension n. So we can also think it like an n by 1 matrix. Now, let's define. define the directional derivative. So last time we defined it, so this time we'll just use the formula. So directional derivative in P, again, in the direction P, so P is in Rm, and the length of P is 1, so denoted by P sub P of F, and it is defined by the gradient of F transpose P. So or we take the inner product between these. So now we're going to demonstrate why it is the case that the direction of gradient is the direction at which the function increases the fastest. So think about, if we have played with any, these optimization algorithm first, we've heard the term gradient descent, and so basically it's our variable subject, subtract a step size multiplied with the gradient. So basically we move along, the direction of negative gradient. And why we're doing that? Why we don't, follow other directions? So the reason is simple. We explain using directional derivative. Okay. So let me first let's do this. So this is gradient of F inner product with P. So what happens is we do the following. So this is the inner product. What we want to do is every vector, no matter what, can be rewritten as its magnitude. So this is its magnitude times a unit vector that is magnitude less and represents its direction. So this is a unit vector. This is a unit vector. So this is unit vector representing x's direction. Okay. And we cannot do the same. Okay. So it's a magnitude of f, which is a scalar, and now it is gradient of f divided by the magnitude of the gradient of f. Okay. So, moreover, it's dot product with magnitude of p times p divided by p's magnitude. But there is a funny thing about this, that is, I mean, this is 1. Okay. But we only want to get rid of this one. All right, so now it becomes the magnitude of gradient of f. And then this part is, so we keep track of all the vectors. So this is the vector, this is the vector. So this 1 over this thing is the scalar, and 1 over this thing is the scalar. Okay. So what happens is the dot product or the inner product is done between these 2 vectors, and these 2 are just coefficients. Okay. So then it becomes gradient of f multiplied with the magnitude of p, and then gradient of f inner product with p. So this term in 2 dimensions. So in n dimension, we can still define something like this. So in n dimension, this term is called the cosine similarity between this vector and this vector. So this term is defined as the cosine similarity between gradient of f and p. The gradient f is our gradient, p is an arbitrary direction at our disposal. And in 2D, this is exactly the cosine theta between the 2 vectors. So this equals cosine theta. And theta is the angle. And by angle, we mean, so because we have 2 vectors, right? So we have actually 2 angles between them. Okay? So we choose the angle that is between 0 to pi. Okay. So theta is the angle between, so theta is the angle which is in 0 to pi between gradient of f and p. Okay. So at a point, this guy, the directional derivative measures how fast this function changes. For example, at a point, x equals a, so dp of f a, this means we take the directional derivative first, and we evaluate that at x equals a, so it basically measures the rate of change of f at x equals a in direction p. Okay. So now let's look at the formula. So in 2D, so let's use 2D as the example. As example, p f of a equals gradient of f at a's magnitude times cosine theta. Theta is an angle from 0 to pi. Okay. And cosine theta, of an angle from 0 to pi achieves its maximum at theta being 0, and achieves its minimum, which is -1, at theta equal pi. Okay. So, okay. And what does theta being 0 mean? Is theta being 0, this means P is in the same direction as gradient of x. Okay, so this tells us one thing. That is, the rate of change so this is because cosine theta changes from -1 to 1. So this quantity right here, the magnitude of gradient of f, is the biggest rate of change we can get at a specific point. So if we change the testing directions. So now this testing directions, now we can see that the directional derivative at a specific point, achieves its maximum value. Okay. So when theta being 0, so which means the function increases fastest in the direction of gradient and achieve its minimum when theta equals pi. So this is equivalent to saying the function value decreases fastest in the direction of negative gradient. Okay. So here's a question. Yeah.
That's the same, basically the same as what you already know, right?
Yes.
Just opposite, like opposite.
Yes.
Okay, great.
So increases fastest in the direction of gradient is the same thing as decreases the fastest in the direction of negative gradient. So we asked our question, we found the direction. Okay, so think about gradient descent algorithm. So think about the gradient descent. So this is like a sneak peek of what we're going to learn, next week. So a gradient descent algorithm is we follow the direction of negative gradient to minimize the function. I mean, we're on the right track, right? It's like it's like so if we it's like we're climbing downhill. We want to follow where, so we put a ball right in the downhill. We just want to follow. If we want to get to the bottom faster, we just follow the ball, follow the physics. So. But here's the question. So when initially at a point x, okay, and we want to follow the direction of negative gradient to get to a new x, so we subtract, okay? So we move in the negative direction with a step size h. How to choose h. All right. So we have established the fact that the negative gradient decreases fastest, right? But how far we should move in the direction? Think about this problem. Why it is so why we should care, why we should care. Okay. So motivation. So again, our famous friend, the quadratic function in 1D. Think about initially right here. Let me say this is x equals to 5. So at f equals 2, so I'm using a gradient notation. Okay, even it's 1D, but it's downward compatible, so it's fine. So gradient is nothing but 2x, right? So negative gradient is negative 2x. Okay. So at the point x equals 2 is just a negative 4. Okay. So we're starting at this point, so x equals 2 gets this x minus an h times, so this is our x, right? This is our previous x. And we want to get a new x. So that our new x, so we hope so what we hope is our new x, which we call x1, so we can call this x sub 0. We hope x1 equals 2 subtract this is nearer to x star than x0. Now think about this dilemma. So for example, when we optimize a machine learning model, we normally choose the step size super small, like 10 to the negative third power, 10 to the negative sixth power. But if we choose h too small, if we choose h to be 0.001, I mean, we move only a tiny bit right here. So maybe here, So it's like, it's pretty inefficient. However, there's a however, that if we choose our step too big, so for example, when we let our step too big, for example, right out here, okay? This is negative 4, right? So negative 4. If we choose h to be 1, what happens is our x1 goes here. Okay, so right here. So our x1 becomes negative 2. We take the negative gradient at negative 2, we get positive 4. So we apply this gradient descent algorithm again. We're bumping back to this point. So our iterative algorithm becomes, okay, so we start here, and we get here, and we get here. So we can never reach this minimum. So like I said, this is the motivation of why we should study how do we choose the step. Okay. And so in next week we will learn how do we choose the step based on the eigenvalues of Hessian matrix. All right. So I mean I want to keep the first week kind of simple. So that's it for today. So let's stop here. And be sure to check the